Welcome to the Explainer. Right, so today we're giving your physics toolkit a massive upgrade. We are taking the entire, sometimes intimidating world of kinematics, which honestly is just the study of motion, and we're breaking it down into really simple, incredibly powerful tools. We're going to journey from just basic, everyday observations all the way up to the kind of advanced calculus that literally lets you predict the future of a moving object. So get ready, because you're about to see the world in a completely different way.
Okay, let's take a quick look at our mental roadmap for today. We're hitting motion and reference frames, then displacement, velocity, and speed. After that, we'll unlock the calculus of motion, derive the famous equations, apply them to motion under gravity, and finish up with Galileo's law of odd numbers. Let's dive into this.
So, are you actually at rest right now? Think about it for a sec. When you're fast asleep early in the morning, dreaming away, you feel like you're perfectly at rest, right? But then, out of nowhere, your mother's flying chabal, the classic slipper, comes zooming toward your head, and boom, suddenly you are very much in rapid motion. It's a funny example, sure, but it hits on a really serious physics concept. The states of rest and motion aren't always as simple as they first appear.
To really grasp this, we need tool number one in our upgraded toolkit: observation, motion, and reference frames. This brings us straight to the idea of a frame of reference. Picture this: you've got two friends, Chintu and Mintu. Mintu is standing perfectly still on the side of the road, just chilling. Chintu, meanwhile, is inside a car driving past him. Now, if you're standing on the road right next to Mintu, you totally agree he's at rest. But if you change your frame of reference, say you're sitting inside Chintu's moving car, looking back out the window, Mintu actually appears to be moving backward. This is the absolute core of relative motion. The exact same person is at rest in one frame and moving in another. It's all about where you're measuring from.
Okay, so once we've observed the motion, we have to measure it. Moving on to tool 2, measurement, displacement, velocity, and speed.
Now, this is where a lot of people trip up. Please don't confuse distance with displacement. Distance is the actual winding path you take. It's like wandering around the neighborhood with your friends before finally heading home. It's a scalar, meaning it only has magnitude, and it is always positive. Displacement, on the other hand, is the shortest straight line path from your starting point directly to your ending point. It has a specific direction, which makes it a vector. And here is the kicker. Displacement can literally be zero. If you walk in a giant circle and end up exactly where you started, your distance might be huge, but your displacement is a massive zero. It can even be negative if you end up behind your starting line.
Finding the distance on a circular arc, piece of cake. It's just the radius times the angle. But finding the straight line displacement between 2 points on a circle, that requires a neat little trick. If you draw a perpendicular bisector to form a triangle, you can just apply some basic sine trigonometry. The result is this brilliant formula: 2 times the radius multiplied by the sine of half the angle, or 2r sine theta over 2. Seriously, keep this in your back pocket. It's an absolute lifesaver for complex problems.
All right, let's talk speed. Imagine this legendary, unstoppable car. Let's call it the Legend Alto, just cruising straight down the highway at a perfectly smooth, impossibly fast, constant pace of 500 kilometers per hour. If that speed literally never changes, you've got uniform speed. But realistically, when you're in traffic, you're constantly mashing the brakes and then the accelerator. Your speed is jerking around, changing every single second. And that, my friends, is non-uniform speed. Because speed is constantly changing in the real world, we almost always need the average speed. The absolute unbreakable golden rule here is that average speed is always total distance divided by total time. Whatever you do, do not just add two speeds together and divide by 2. For example, there's this classic round-trip problem they love to put on tough exams like the JEE. It asks for the average speed of going somewhere at velocity 1 and returning at velocity 2. If you just plug the separate times into our core formula, you get this amazing shortcut: 2 times v1 times v2, all divided by v1 plus v2.
We've got basic measurement down. Now let's bring in the heavy machinery. Tool 3, advanced prediction, the calculus of motion. Look, don't let the word calculus scare you off. It's basically just a cycle of operations. If you have an equation for displacement and you differentiate it with respect to time, you get velocity, which is literally just finding the slope on a position time graph. Differentiate that velocity and you get acceleration, which tells you how fast your speed is changing. And the absolute beauty of this math is that it works in reverse too. If you integrate acceleration, meaning you find the area under the curve, you step right back up to velocity. Integrate velocity and boom, you step back up to displacement. Now what's really cool is how simple the rules actually are. derivative of a constant number standing all by itself? Always 0. For a variable with a power, you just multiply by the old power, then subtract 1 from the exponent. And integration is literally the exact opposite. You add 1 to the power, and then divide by that new power. I'm telling you, with just these 3 little rules, you can solve the vast majority of kinematics problems.
But hey, what if you need to find acceleration, and the problem simply doesn't give you time? What if it only gives you velocity in terms of displacement x? Well, here is an absolute physics cheat code. We start with our standard formula, a equals dv by dt. Then we multiply both sides by dx over dx. Since that's just 1, we aren't breaking any math rules here. By rearranging the terms and recognizing that dx by dt is just velocity, we end up with a brand new formula. Acceleration equals velocity multiplied by the derivative of velocity with respect to displacement. Seriously, memorize that one.
So what's the ultimate application of this fancy calculus toolkit? Tool 4, Universal Rules, Deriving the Equations of Motion. Let's actually walk through exactly how we get the very first equation of motion. We start with our calculus definition. Acceleration equals the change in velocity over time, or a equals dv over dt. Rearrange it so acceleration times dt equals dv. Then we apply our integration snake to both sides. We integrate time from 0 to t, and we integrate velocity from our initial velocity u to our final velocity v. When the dust settles on all the algebra, we get the legendary formula v equals u plus at. Calculus logically proves that this rule works universally. It's not magic, it's just pure mathematical certainty.
These equations also save us from falling into common traps. Like, there's this classic trick question that asks for the distance traveled in the 5th second. Notice I didn't say the distance at 5 seconds. It wants to know exactly how far the object traveled during that one specific second, right in between second 4 and second 5. The logical fix? You calculate the total displacement for all 5 seconds. Then, you calculate the total displacement for the first 4 seconds. Subtract the second value from the first, and you are left with exactly what happened during that 5th interval.
Tool 5. Universal Rules. Continue. Let's look at motion under gravity and bring all this complex math back down to Earth. Literally. You have to be absolutely ruthless with your sign convention here. When you're dealing with gravity, any direction pointing up is positive. Any direction pointing down is negative. And because the Earth is completely unforgiving and is always pulling things downwards, acceleration due to gravity is always negative, whether you throw a ball up or drop it down. Don't forget that. This rule creates 2 extremely predictable scenarios. If you simply drop a ball from a height, its initial velocity is perfectly 0. Using our derived equations, we can find out exactly how hard it will hit the ground. It's the square root of 2 times gravity times height. Conversely, if you throw a ball upwards, it starts with maximum velocity. But right at the very peak of its throw, right before it falls back down, its final velocity becomes exactly 0. And knowing that lets us easily calculate the max height it reaches and exactly how long it takes to get there. And just to keep the math somewhat clean during these gravity calculations, we usually round the acceleration constant due to gravity to negative 10 meters per second squared. Remember, that negative sign is non-negotiable. It represents the Earth constantly pulling you down. Finally, we've arrived at the last tool in our kit, Tool 6, the magic ratio. Galileo's law of odd numbers. Hiding deep inside all this complex algebra is a surprisingly simple pattern. Centuries ago, Galileo realized that if you drop an object from rest, the distance it falls during consecutive, equal intervals of time, like the first second, the second second, the third second, always follows a very specific ratio of odd numbers. It's always 1 to 3 to 5 to 7, and so on. Let's actually prove it real quick using that nth second trick we learned a minute ago. If we drop a ball in the first second using our gravity formula, it falls 5 meters. In 2 total seconds, it falls 20 meters. But the distance in just that second, well, 20 minus 5 is 15 meters. In 3 total seconds, it falls 45 meters. The distance in just the third second, 45 minus 20 is 25 meters. So our distances are 5, 15, and 25. Divide them all by 5, and what do you get? 1, 3, 5. It just brilliantly illustrates that underneath all the scary equations, the universe actually runs on some beautiful, simple rules. So we've upgraded everything from basic observations all the way up to mastering calculus and uncovering Galileo's hidden ratios. You now have the fundamental framework to truly understand motion in a straight line. But it leaves us with an incredible thought to end on.
If just a few simple rules of calculus and gravity can perfectly predict the path of a falling stone, what else can this physics toolkit unlock for you in the universe? Keep questioning, keep observing, and I'll see you in the next explainer.